Okay, hello everybody, and welcome to Papa Lim Physics Classroom. And today we'll be going through another prelim paper for physics. Okay, the same as before, the video will be a long one because I'm going through every questions in the paper too. Okay, so if you have any particular questions that in mind, okay, remember you can just skip through the video and just go to the exact location where I'm going through the question. Okay, so if you have not have the paper, okay, I'll leave the paper in my Google Drive, and the link is in my description panel there. So by all means, go and download the paper and give it a try. Okay, so those who have tried, okay, we'll go through the paper together and to look at what are the mistakes that you may want to touch up and what are the common pattern of the questions that we actually encounter. Okay, well, without delaying, we will look at the paper 2 for CHIJ. Now, paper 2, question 1. Okay, question 1 is it's on kinematics, but it's actually quite a good question in the sense that the way they ask is actually quite different. Okay, it go to our basic of looking at distance, displacement, and even speed itself. Okay, now I have two balls. No, I have one ball. Okay, traveling down the slope at different timing. Okay, one of the important factor for this question is to look at the time. Okay, the time here is important. Okay, for question figure 1.1, how does it show that it's accelerating? Now we go back to the basic of accelerating. Accelerating implies that the velocity of the object is actually increasing. And when the object is increasing, how do you know that the velocity is actually increasing? One of the most obvious one is whereby the distance of the object or displacement of the objects, okay, is increasing at an increasing rate. Okay, so which means the displacement is actually getting faster at an increasing rate. So what does this mean? It means that the distance between each interval or each seconds, the distance is getting bigger and bigger and bigger, which is what this diagram is trying to describe to us. So based on the picture of the ball at different timing, I'm able to see that the distance traveled, important is per unit time, is actually increasing. And to be exact, it's actually increasing at increasing rate. Okay, now, how do I calculate the average speed of the ball between time 1 and time 3? Remember, total, when we talk about average speed, is about total distance and total time. The time taken here is a small trick. Remember, the time taken is time 1 to time 3. So it doesn't mean that 3 seconds has passed. Okay, time 1 to time 3 implies that actually 2 seconds has passed only. Only 2 seconds has passed. And what is the distance between time 1 and time 3 seconds? Time 1 is here, which is 20. Time 3 is here, which is 100 meter, 100 cm. So at time 1 is 20. So you'll be 100 cm minus 20 cm. So you give you 80 cm. So that's why when we look at the speed is total distance divided by time, you will give us 40 cm per second, okay, which is the answer given here. So just take note of the small subtle booby trap that we're looking at. Okay, it's time 1 second to 3 seconds, not time 0. So just take note where is the starting point. Now for part C now. Part C now, the question mentioned two forces. Okay, one is air resistance and one is weight. So then the question asks, as the ball is rolling down, what is actually happening? Okay, one thing for sure is that mass or weights, okay, it has everything to do with your mass. Okay, so if my mass remains the same, my gravitational field strength, which is Earth, okay, remains the same. Okay, so which means mg will be constant. So this will imply that my weight actually will remain the same as I roll down the slope itself. On the other hand, if you look at air resistance here, yes, linked with speed or the velocity, to be exact, is the speed of the ball here. Okay, so how does the air resistance changes? Remember, one of the subtle relationship that students have to know is that how speed changes with air, how air resistance changes with speed. Okay, so take note is that as speed increases, your resistance will actually increase. Okay, it's not proportional, but they are always in the same direction. So as my speed increases, my air resistance will increase. In fact, so the resistance actually get higher and higher, bigger and bigger as the speed of the ball increases. Okay, so one of the things that we notice that the resistance actually increases because the speed actually increases with time. So the bigger the speed, the bigger is the air resistance. Now, for question 2 here, we have is a kinematics question, but one interesting thing that we are looking at is for this question, usually kinematics question, the graph given is always velocity time graph or speed time graph. But for this particular question, we are looking at is actually distance time graph. Okay, remember this distance time graph, so don't mention anything about acceleration deriving from the graph. Now, the other interesting thing that we have from this question is that the train P actually starts 10 minutes later. So that's why your graph P actually starts 10 minutes later at this particular point here. Now, for question A, he mentioned how do we know that train P has a greater speed than Q? And the emphasis is from 2.1. Now, when we look at distance time graph, one of the important things that we need to know is that how do we derive information about the speed? And how do we derive information about speed is actually using the gradient. The gradient of the speed time graph actually represents the speed. So here, we must pay attention to the steepness of the gradient or the line itself. So P, which is a greater gradient, or what we call a steeper gradient, will actually means that the speed of P will actually be higher than the speed of Q. Okay, that's what we mean. That's how we use figure 2.1 to derive information about the speed. Because ultimately, for distance time graph, where we derive information about the speed, what we are looking at is actually the gradient of the line. Okay, so this is one important factor that students have to know, the concept of the way that we derive. We use distance time graph. And from here, we know that the greater the gradient, the greater is the speed of the object. So that's why with P having a steeper gradient, it will mean that the speed of the PQ will actually be higher. And thus, this is what we mean by representing the answer from the graph. Okay, so this important thing is student must remember the right gradient. How do we derive speed? Is from the gradient. And how do we know P has a greater speed? Because the gradient of P is bigger than gradient of Q. Okay, that's what we are trying to derive. Now, what's the distance between the two stations? Okay, one of the important things that you have to take note is the distance between the two stations is when I arrive at the station. When I reach the station, both P and Q are stationary. So which means that how do I know P and Q has reached the station? Is whereby P and Q actually stops moving. So this information will tell us that as P and Q stop moving, it will mean that P and Q has reached the station. And from the graph, you will know that P and Q stop moving implies that the P and Q is always at the same distance as time passes by. And one important information that we see here is at this particular point, P stops at this particular timing, at this particular location. Likewise, for Q, he also stops at this timing, at this same distance here. Okay, so this will tell us that P and Q are actually at the same place, which is at the distance 120 kilometers away. So which means that from the starting point at 0, let's say for Q, I end up at here. For P, I start here, 10 minutes later, I end up at here. But both of us will end up at the same location, which is the station, end of the station. So this will tell us that the distance between them will be 120 kilometers. Speed of Q, of course, okay, where it's moving, which is the gradient. Now, for speed of Q, okay, I'm looking at the gradient of the line here. So basically, I need to find the rise and the run for the particular line here. So for Q, I will need the distance, or what I call the rise, which is 120. And I actually need the timing here for where it reaches this distance of 120, which happens to be 90 minutes. So remember, the question specifically asks for kilometer per hour. So I will need to convert 90 minutes to 1.5 hours. Okay, so that's why I have a 1.5 hour here at my denominator when it uses the formula. Okay, so 120 divided by 1.5, okay, it will give you 80 kilometers per hour. If you don't like the way this is presented, you can actually look at this. You can say that the gradient, okay, which is the speed, okay, which is followed by speed, which is actually rise over run, which is 120 kilometers divided by 1.5 hours. So it will give you the same answer, 80 kilometers per hour. Okay, so same concept as before. What we are looking here is that the gradient of a speed time graph actually give information about the speed of the object. Okay, so this is one important fact that we are targeting for students, whether he or she, the students, know how to manipulate distance time graph or even other velocity time graph. Now another train R, okay, makes the same journey. Okay, makes the same journey. Remember, this is one keyword. So it means it will reach 120 kilometer, and it's the same speed as P. Now, same speed as P implies one important information. Same speed implies same gradient. That's what information that the marker needs the students to infer. So which means that if P and R has the same speed, this will imply that both of them actually have the same gradient. Okay, so the line that you are supposed to draw is P and R supposed to be two parallel lines with the same gradient. So this is what we mean by, it might be a bit too small. Let me zoom in. Yeah. So which means for R, for P and R, the gradient must be the same. So meaning there must be two parallel lines. The important thing is they reaches the same journey. So which means they must stop at 120. Okay, parallel line. So that's the second thing they must achieve. What about the third information? Now, the third information that we have is that it operates 30 minutes later than P. So if P starts at 10 minutes here, 30 minutes later here will be plus 30. So R will actually starts at 40 minutes. Okay, and it reaches 120 kilometers because it reaches the same station. So it will give us, with these three conditions, you will find that with these three conditions, okay, you'll find that the only line that satisfies will be this particular line that we are looking at. So R, this will be the line to represent, this will be the distance time graph for R itself that satisfies all the three conditions, reaches 120 kilometers, same speed, or aka same gradient, and 30 minutes later. Okay, so just take note of the distance time graph. So I would say that for this particular questions, students who are well versed with speed time graph and distance time graph shouldn't have a problem. Common mistakes I might think students encounter is actually misreading the graph. Instead of looking at it as a distance time graph, the students might interpret this as a velocity time graph or speed time graph, and as a result, the approach will actually be slightly different. Okay, so just take note of what the question is asking for and be alert to small changes. Question 3 is what we know as your forces, or what we call your tip-to-tail drawing, or even parallelogram method. Okay, for these particular questions, okay, I won't elaborate much because I will find that it's quite a standard question for summing of forces, for resultant forces. So I will leave the link to my parallelogram method and tip-to-tail addition of forces, okay, in the link above. So if you want to revise, if you would like to revise on this particular method, okay, you can click on the link and actually revisit the video. Okay, so if not, I'll leave the answer here. Thereafter, you can take a look. Okay, if you have any questions regarding this particular question, okay, just leave your question in the comment bar below and I'll get back to you ASAP. Okay, if you need me to create a video answer of how to solve this particular question, do let me know also. Now, if not, we'll look at 2B. Now, based on the question is that the engine of the car is not operating and is stationary, yeah, and he's moving in a straight line, okay, and it's moving at a constant speed. Okay, important word is a constant speed. Now, when we talk about constant speed, one of the first thing that will ring, or that should ring in the student's head, it should be constant speed. It means that the acceleration of the object is actually 0 meters per second square. Okay, so after that, what does this tell us? Okay, now, why is it moving in straight line at constant speed? Because what happens is we are able to derive that the acceleration of the object is constant, is 0 meters per second square. And based on this information, it will actually tell us that the resultant force of the object is actually 0. And once I know that the resultant force on the object is actually 0, it will imply that the forces actually is a balanced system, which means that the forces acting on the object is actually 0. The two forces acting, the resultant force acting on the type of boat, and the friction between the water. So in this case, the resultant force, okay, which is the green color, okay, it will be the same as the frictional force between the ship and the water. Okay, and because they are the same, the resultant force between the two forces will actually be 0, and it will give us a resultant force acting on it is 0. Okay, so from this information, how do we derive all this answer? Is actually from the fact that the first clue that the question tells us is about the speed of the object itself, which is constant speed. This will actually lead us to the next important information, whereby the ship is actually moving at zero acceleration. Okay, constant speed, zero acceleration. And this will lead us to be able to deduce that the resultant force acting on the ship is actually zero. And this will lead us to the final inference to say that the two forces acting on the boat itself is actually equal and opposites. Okay, so this is how I derive information using Newton's law. And to be exact, here what we're looking here is Newton's first law. Now, for the next part, question 4. Okay, question 4, we have a plank. Okay, we have a plank with two supports. Okay, now, one important thing here is that the center of gravity is here. And we are given a dimension of the plank itself. And then after that, we are looking at is the density of the plank itself. Okay, density, remember the basic formula we are looking at. Density is mass over volume. So this is the basic formula that I have. Okay, we are given the mass, which is 23 kg. Remember, it's in kg. Yeah. The volume is given here. Okay, length, breadth, height. Okay, everything is given. So you can actually easily find the volume of the object. Then after that, you just substitute the value inside the formula, and you'll be able to derive the answer to be 730 kg per meter cube. Okay, all in 3SF in SI units. Now the center of the plank. Now based on this information, the center of the gravity is at the middle of the plank. Okay, remember the whole length is 3.6 meter at a distance 1.3 meter from each support. So which means that this segment here is actually 1.8 meter. Information, whether it's useful or not, I will not know, but I do know that middle of the plank is actually 1.8 meter. Now, calculate the weight of the plank itself. So the weight of the plank is at the CG. Okay, so the weight of the plank is at the CG. So this is the weight of the plank I'm looking at. Okay, so weight, the formula is mass times G. Okay, gravitational strength given 10 Newton per kg. Mass is given 23 kg up here. Okay, so mass is given here. This is 23 kg. So that's why I got 23 here. So simple thing, just put in the formula, you get 230 Newton. Now the moment due to the weight about the right hand pivot, the right hand support. The right hand support means this is the support I'm looking at. Okay, so if this is the force I'm looking at is the weight of the plank. So the perpendicular distance I'm looking at is actually the perpendicular distance between the force and the plank itself. So which is how much? Which is 1.3 meter, which is given by the question already. So force times perpendicular distance, it will give us an exact answer, a nice answer of 299 Newton meter. So this will give us the what we call the anti-clockwise moments. Okay, about anti-clockwise moment about the right-hand side pivots. Okay, so this will be the clockwise and the anti-clockwise moment. Now, based on the question now is if the painter is moving to the right of the plank now, and the plank will start to rotate clockwise. Okay, so now if the painter is moving to the right side, so this painter is moving to the right side. Okay, so you'll be stepping on somewhere, let's say on the right side, you'll be somewhere here. Okay, so the painter will be somewhere here. So this is the weight of the painter. Okay, so this is the weight of the painter, you'll be on the right side. Now, what will happen? It will start to rotate. And why does the plank start to rotate in this case? Okay. Now, what happens is as the painter move further to the right, okay, the weight will be clockwise about the right-hand pivot. Why? Because you take a look, if the weight is here, if the painter is on the right side of the support, there is a perpendicular distance between the painter. Okay, there is a perpendicular distance between the painter, the force, the weight of the force, with the pivot himself. So there is a perpendicular distance. Okay, and when you have a force and perpendicular distance, you actually have what we know as a moment. In this particular case, this will be your moment of the painter, which is actually clockwise. Okay, so this is what I mean by telling the marker, so clockwise moment. And what happened is you have a clockwise on the right side. You have a clockwise moment now. But what happened? You find that the painter is actually much heavier than the person, than the plank itself. Because why? The plank is only 23 kg. A normal size human being, a normal adult, will roughly weigh around like 40 to 50 kg and above. So definitely the force, the clockwise moment, okay, will definitely be larger. The clockwise moment will definitely be larger than the anti-clockwise moment of the plank. Okay, so now when your right side, the clockwise moment is larger than the and then the anti-clockwise on the plank. And what's the result? Is that the plank will topple. Okay, so which means that you take a look, between the green color moment is actually much higher, much larger because of the size difference in size of the force itself. So the painter is much heavier than the plank. So the moment the painter step to the right side, your clockwise moment will actually be higher than the anti-clockwise moment by the plank itself. And as a result, the plank will actually rotate and the plank will actually drop off, or to be exact, the painter will fall down. Okay, so just take note of how we actually analyze the rotations based on the movement of the weight and the movement of the perpendicular distance. Okay, so important keywords we are looking at is actually where we identify the clockwise moment, and followed by which moments is actually larger than the clockwise moment, is actually larger than the anti-clockwise moment. Now for question 5 here, this is a question regarding energy. Okay, it's actually quite an interesting question where, especially part A, okay, I actually have some difficulty in part A until I notice the clue given by the marker. Now, first clue that I noticed is that the clue the marker gave us is actually up the hill. Okay, so we are looking at energy changes as I cycle up the hill. Okay, so this is the point that we are referring to. So from the bottom all the way up to A. Okay, so at point A, I will definitely, because of the height here, the energy possessed here will be actually potential energy, definitely gravitational potential energy. The other clue that the marker actually gave us is actually at constant speed. So which means that the speed at A and the speed at the top, they are actually the same. So which means the speed at A is actually equal to speed at the top. Okay. In other words, when we look at speed, the energy that involves speed is what we call kinetic energy, which is half mv squared. If the speed of both locations is the same, it will mean that the kinetic energy at A is actually equal to the kinetic energy at the top. Okay, so which means the kinetic energy actually remains the same, which means that there isn't any increase in internal energy, in kinetic energy, which means there isn't any conversion of kinetic energy. Okay, so this is one of the clues that we actually that is actually highlighted to us, which is at the beginning and at the end, none of the energy is actually converted to kinetic energy because it's actually traveling at constant speed. In other words, when you convert the energy, when you have energy converted to chemical and potential energy, okay, why chemical is because of the third clue that the question gives us is she, the person herself. The energy that the person possesses is actually what we know as the chemical potential energy in the body, energy in the stomach. So where she get all the energy from. It could be from the food that she ate, or it could be from the chemical energy that is actually stored inside the body. So that's why I know that based on the clue, I will know that the starting form of energy at the initial stage is actually chemical potential energy. Okay, because of the references to the person himself or herself. After that, I move up to the top of the hill, whereby no kinetic energy is converted. So some of the energy is actually converted to where? Some of the energy is converted to the potential energy himself, okay, to the top of the hill himself. And similarly, when I move up the slope, where there will definitely be some work done, there will definitely be some sweating, some sound being produced. And as a result, I will have thermal energy and sound produced. So from here, we are able to deduce that the actual energy coming from the initial stage, which is chemical potential energy, is actually totally converted, okay, to your gravitational potential energy and your heat energy or thermal energy and your sound. So as I cycle up, frictions in the bicycles, friction in the gears, okay, or it could be friction in the floors along the tracks, between the tires and the track itself. And after that, along the way, maybe the bicycle produce some sound or these things. So all the energy will be converted to these small areas. Now, how about part B? Part B talk about the conservation of energy for journey A and B. Journey A is here, journey B is here. So one look, you will know that actually A and B are what we call at the reference point, whereby the height is actually 0 meter. So both of them, B is actually height at 0 meter. So which means that we can actually deduce that both of them, the potential energy at this stage, okay, at this A and B stage, at both stages are actually the same amount, which is actually 0. Similarly, based on the question did mention that it's always traveling at constant speed, okay, which is what we deduce at part A. And we also, in this case, we also know that the kinetic energy at A and at B is actually the same number, which means no energy has been converted to kinetic energy because it always remains at the same speed. So which means there's no energy converted to kinetic energy. But one thing for sure is that the cyclist definitely actually spend energy, actually uses energy from his chemical potential, from his stored energy in the body. So there is definitely input. So on the left side here, there will definitely be input is what we call your chemical potential energy. So this is the input here. So when you have, based on law of conservation of energy, total input must be equal to total output. But in this case, my output, there isn't potential gravitational potential energy, there isn't kinetic energy. So where has the energy gone to? And based on analysis, you should know that if I cycle up, there definitely be frictions along the ground, friction along the gears, and definitely sound make along the way. So as a result, I will know that I will be able to deduce that all the energy from the body, from the cyclist, will actually converted to thermal energy, and it could be sound energy also. So in other words, the chemical potential energy I have is actually converted to your thermal energy, or some we say heat loss, and maybe it could be your sound energy. Okay, so in this case, this is where the conversion of energy is still valid, but it's just that it's converted from one form to another form. Chemical potential energy in this case is not converted to potential nor kinetic energy. It's actually converted to your thermal energy and sound energy. Okay, but in other words, your law of conservation of energy still obey. Now, for the last part, it will be an easy one. Last part will be the height above A to calculate the potential energy. Now, based on the question, it says that the cyclist potential energy increases by 5,700. So automatically, you will know that the GPE actually is 5,700. And I need to know the height of the cyclist. So it's a simple substitution of formulas, mgh. Oops, sorry. And I will want to find h. What is h? And if you do a simple manipulation of math, you'll find that the h will actually be 9.5 meter. Okay, quite easily done. Okay, now let's look at question 6 now. Okay, question 6 is I would say it has to do with it's a pressure volume temperature, it's a gas law question. Okay, now you have your syringes here. Your syringe. The important thing about this particular question is that there is actually two situations that is ongoing at the same time. One is that the fact that the temperature is decreasing. Then after that, you actually have another situation that the piston is moving inwards. Okay, so you have two different situations or two related situations. Okay, first you have the syringe being cooled down. Then after that, the piston actually is moving inwards. Okay, so these two were amount to two different scenarios or two different cases. Now, let's take a look at what is happening at the beginning. Now, for gas law, when your temperature is decreasing, okay, based on what we understand is that when your temperature is decreasing, you will find that the particle is actually moving slower and slower. Okay, so as a result, what you are looking at is that there will be less collisions occurring in the system. And at the same time, when there's less collisions, okay, you will have what we know as your pressure will actually decrease. Okay, this is what happened in the first scenario when temperature actually decreases. Okay, so this is first scenario. Okay, now what happened to the second scenario? In the second scenario, when the piston is being moved inside. Now, what happened is after the pressure actually has decreases. Okay, after the pressure has decreases, you'll find that the pressure in the syringe in the interior is actually lower than the atmospheric pressure outside. And now it's because there is a difference in pressure whereby the external pressure is actually higher. External is actually higher than the interior. So what we have is that there will be actually a force exerted onto the particular piston. And thus, it will cause the piston to be pushed inwards. And this is what happens and this is what set off the reduce in the piston moving inwards and what the volume decreasing. So what happens is when the piston actually move inwards, actually we encounter is that the volume available inside actually reduces. Okay, so now with the pressure decrease, in the interior pressure decreases, it causes the piston to push in, and the interior volume actually decreases, and as a result, you'll find that the collisions between the particles actually increases. Okay, now here, one thing to take note is that at this point in time, right, temperature is at this particular instances, at this particular level. So at this point in time, because the volume decreases, the collisions actually increases due to the reduction in space. Okay, so this is because of the volume reducing. So there's lesser space inside the strings itself. And as a result, the collisions between the particles actually increases tremendously. Okay, so this is because of the lack of space now. The average force exerted onto the onto the wall will actually increases because now my collisions happen more and more often. Okay, so despite colliding, exerting at the same force, but now what happens is that my frequency actually increases, and thus it will actually result in the average force exerted on the wall to be increased. And when the force exerted increases, the force per unit area, or what we know as the pressure in the cylinder, actually will increase back. Okay, so now the whole cycle will repeat again. So now when the pressure increases, but what happens is the temperature reduce again. Okay, as it cool down, the pressure will drop back again. So for this whole entire sequence, it ranges from the first scenario, okay, to the second scenario. Then after that, after second scenario, the whole scenario will repeat again. So case one, scenario 2, and the whole thing will repeat. So at this point in time, you'll find that there is actually one interesting pattern that we see. One interesting pattern is that you see that the pressure actually reduce at the initial stage. Then after that, the pressure will actually rise back. So you find that a drop in pressure and a rise in pressure, these two will tend to make the pressure actually even out to be back to the same number. And that number that we are looking at is actually what we know as atmospheric pressure. Because when the piston stop moving, it will mean that the interior pressure, okay, actually will be equal to the exterior pressure. Okay, and what happened in this particular situation? You find that at the pressure of the gas after the piston stops, it actually remains the same, okay, as it is at the beginning. Because every time I drop the pressure will increase back at the second scenario. So every time I drop a few notch, I will increase a few notch at the other side, at the other scenario. So you find that the pressure actually remains the same. What happened to the average speed of the gas molecule? Now, the gas molecule here is throughout the situation, the reduction in speed, okay, the reduction in speed actually rises at the first scenario. Okay, the reduction in speed actually occur at the first scenario, and because the temperature drops, the velocity of the particle actually reduce. And what happened is that the reduction actually is what we know as a permanent thing, because it has everything to do with your temperature. So every time my temperature reduce, my speed will actually reduce. Okay, so at the second scenario where the piston move inwards, remember the collision is increased because there's less space, but the speed of the substance itself actually remains at the same. Okay, so the speed of the particles actually get reduced at the first scenario, and with that same speed, now I travel at a smaller space, okay, smaller volume, the collisions will still increase because of the smaller reduction in space. Okay, and thus this is what we can conclude is that the frequency of the collisions between the particle actually increases because of the lag in volume, because the reduction in volume, not lag of volume, reduction in volume. Okay. The other thing that remain constant that we see is actually the diameter of the gas molecule. Now, throughout the whole scenario, or scenario 1 and 2, you'll find that the speed or the speed and the force exerted, it does have undergo some changes. Even the volume actually undergoes some changes. But one thing that remains the same is that if there is no leakage, the number of particles inside this piston will actually remain the same, and the size of the particle itself will actually remain the same. So that's why we know that actually the molecule itself, okay, nothing will change if there's no leakage. Okay, the size, the number of particles, all this will remain the same. Now, the average distance between the molecule, okay, now the average distance between the molecules is because of the fact that the temperature has reduced and the speed has reduced. Okay, the speed of the molecule has reduced, and as a result, you'll find that at that confined space, okay, at the restricted space, you'll find that the average space between the gas molecule actually reduces by a bit. Okay, and thus, okay, this actually tells us that, okay, gas is actually compressible. Okay, so as it is being compressed, okay, gas is being compressed. Okay, the distance between the gas molecule actually reduces. Okay, this because of compression, and this or what we know as the reduction in volume. So now the particle does not have so much space to move around. So so the distance between them actually reduced by a bit, okay, due to the space constraint. Okay, so with this, you will be, this is how I do about analyzing what actually happens from 90 degrees Celsius to 10 degrees Celsius. What actually happens to the speed of the particles, the force of the particle exerted by the force, the pressure of the force, and even the frequency of the collisions. Okay, this is what we mean by analyzing based on these two scenarios. Okay, the two gas scenarios that's happening. Okay, so like I mentioned before, the clue lies in the fact that there is two scenarios. One is the reduction in temperature. The other second case is a reduction in the volume itself. Now, for question 7 here, 7 here is a EM spectrum. Okay, straightforward, yes, definitely. Okay, so but the main thing that we have for EM spectrum is that students, you need to know what are the arrangements for the EM spectrums in terms of their wavelength, in terms of frequency, and finally the calculation will be the wave formula V equal F lambda. These are the formulas that we use. Okay, so if you know the electromagnetic spectrum, you will know that actually there are some mistakes here, whereby you see ultrasound shouldn't be inside the spectrum, because it is actually, ultrasound should be actually is a longitudinal wave. It's not a transverse wave. Okay, and of course, if you know the sequences, you will know the sequences for infrared and microwave are actually at the wrong side. Okay, so this is what we notice. And of course, for EM spectrum, okay, you need to know all the spectrum, what it contribute to the electromagnetic spectrum. And in this case, you'll find that actually the middle segment here, we are missing one important category of EM spectrum, which is what we know as the visible light. Okay, so you must take note of what is missing in the EM spectrums. So with this, I would say A is fairly simple, and B is even simpler in the sense that it asks, for example, X-rays. Okay, X-rays, one of the common examples that we have is for fracturing, to identify for doctors to actually look at the X-ray film to see fracture. Okay, the other application that we have is actually to use X-ray to check for cracks in the structure. Okay, so whenever I see a crack, okay, maybe the sound, the X-ray will bounce back, so that I will be able to receive the signal to indicate that there is a crack in the wall. Okay, so this is one of the important uses that we have for X-ray itself. Now let's look at question 8. Question 8 is about electrostatic induction and earthing actually. Now for this particular question, is a two-part, part A and part B. Part A actually asks you for the steps or the procedures to charge the sphere negatively, okay, from an uncharged or neutral sphere, a neutral metal sphere. Now, what happened is, for part A, the important thing is the sequence. Okay, when do you bring the rod near, or when do you earth the rod, and when do you remove the rod, and when do you remove the earth wire? Okay, the sequence is important. Okay, so for question 8A, okay, 8A, the important thing is the first step. The first step is to bring the positive charge nearer to it. Okay, bring the positive charge nearer to it, but you do not touch. So and what happened is, in this case, right, when you bring the charge nearer to the sphere, okay, the metal sphere, the charges are free to roam around. You'll find that the charge will actually redistribute themselves. Okay, and that is actually the answer for your part B. Okay, so when your rod is brought near to the sphere itself, what happened is, the electrons, okay, the electrons, this is step 1, corresponds to step 1 now. The electrons in the sphere, okay, will be attracted to the left side of the sphere, okay, because of opposite charge attract. Okay, and as a result, when your negative charge is on the left side, what you are left over here is actually the positive charge on the right side. This is what we have when we look at the first step. When you bring the positive rod nearer to the sphere but not touching, and you will find that the charge on the metal sphere will actually realign themselves, or redistribute themselves, such that the negative charges is actually on the left and the positive charges on the right. Okay, because of positive charge attracts, unlike charges attracts. Then after that, what happened at this instance here, remember, you want a negative charge rod. So you want a negative charge sphere. So what you do now is you actually bring in your earth connection. Okay, so you bring in your earth connection, touching the right side of the sphere here. So upon touching, what actually happens when you touch? Okay, how do we get your positive charge? Is because now when I'm connected to Earth, my electrons will actually flow from the Earth itself. So which means at this point in time, at stage 2, the electrons will actually flow up from the ground up to the rod itself. And the main purpose of the electron coming up is because to neutralize the positive charges. Okay, because unlike charges, the electrons will flow up from the ground, and the electron will flow into the metal sphere, the right side of the metal sphere. And as a result, you'll find that the right side positive charges will be neutralized by the electrons from the ground itself. Now, at this moment in time, remember, you have to take note, you have to remove the connection, the earth connection first. Okay, you have to remove the earth connection. Okay, do not remove the positive rod first. Do not remove the positive rod. You have to remove the earth connection, because the moment if you remove it in the wrong sequence, example, you remove the charge rod first, okay, you'll find that these electrons will actually be neutralized by the earth wire, because the earth wire is actually still connected to the sphere itself. So end up you will have a neutral metal sphere charge again. Okay, so the sequence is important. So once your positive charge has been neutralized, the third step is actually to remove the earth connection. So you should remove the earth connection. Okay, now at this point, remember, your positive charge is still there. Your positive charge rod is still there. Okay, you remove the earth connection, and what you have now is the fifth step here is to actually remove the positive charge rods. So once you remove the positive charge rods, you'll find that the remaining negative charges, okay, they will actually redistribute themselves. Why do they redistribute themselves? Because of light charge repel. So all the negative charges will actually repel to different corner of the sphere here, okay, to the furthest corner of the earth, such that, okay, they will actually keep away from each other because light charge repel. Okay, so this will be the final distribution of your rod itself. This is what we mean by a final distribution of your metal sphere itself. And this distribution will account for the negative charge in the metal sphere now. Okay, so this is what we mean by charging by charging by inductions, whereby you actually charge the rods, charge the sphere into a so-called desired charge, okay, using the charge rods. Okay, whether it's a negative charge rod, okay, or whether a negative charge rod or whether a positive charge rod, you can actually bestow charges. Okay, you can actually change the uncharged metal sphere to a charged metal sphere of the charges that you want, okay, just by using earth rods, okay, and earthing wire at the correct sequences. Now, the last question is a straightforward one, okay, where you have 2.5 nano charges. Okay, and the process takes 4 milliseconds to calculate the currents that is produced during these instances. The formula that we use, I will say that everyone should be familiar with it, whereby Q is equal to IT. I would say the tricky part here is to actually take note of the prefixes nano. Okay, what are the prefixes for nano? You must know that it's actually 10 to the power of -9. Milli, okay, you must know it's actually 10 to the power of -3. So if you are aware of the prefixes, I would say it's just a simple calculation whereby you can leave it to your calculations, and from there you can generate the answer straight away. So this will be quite easily done. Okay. Now for question 9. Question 9 is a circuit breaker. It's a design of a circuit breaker. Okay. Now, one thing to take note is that usually the parts label here are important stuff. Okay. Why? The labeling here usually are hints to tell the students that if you need to describe the working mechanism of this particular device, okay, you are advised actually to use all those label words. These label words also serve as a guiding point for the kids, okay, so that they know what to write, what to use, and what are the actual procedures. Okay, so like some clues that the marker gives to the students. And true enough, you'll find that actually the question actually asks you to describe, okay, describe how it works. Okay, when a large current enter the coil. Okay, when the large current enter the circuit now, okay, now when the large current enter the circuit, the easiest one is to track what is happening to the, okay, but in sequence. So when the current is entering here, okay, so when the current is entering here, okay, you will first go through the coil first. Then after that, the pivots, okay, spring, all this will take into effect. Okay, so now how do we use these labeling, okay, as a guide for you to actually describe the whole procedure? Okay, let's now take a look. Okay, so when the large current actually flow through the coil, remember for coil, the clue whenever we use coil, the clue that we are telling the students actually that to take note of that the coil can be an electromagnetic when the current passes through it. As for pivot, okay, if for iron core, definitely iron core and coil, they are together, whereby the electromagnet is used to attract certain things. Okay. When I say pivot, when I use pivot, I'm actually trying to hint to students that actually that particular devices or that particular location is allows some rotation. So it could be like rotating upwards or downwards. Okay, so there will be some rotation at this pivoting point. That's why I'm trying to hint to the students that it has something to do with rotating. Spring, spring. Whenever I use a spring, I actually want the students to take note that spring, it has something to do like bouncing back to the original location, or it's being like it being pulled back or it pull forwards. Okay, there's some bouncing or returning to the original position or stretch positions. Okay, so that's what I mean by we're talking about your spring. Now, when you look at your springy matter, whenever I use springy matter, I'm actually trying to hint to students that actually this piece of metal there's some flexibility, whereby the spring actually will be like may swing left or right or up and down. So that's where the springy metal, the word springy, is trying to hint to the student. Fixed point, in this case, when I use fixed point, I would say that I'm trying to tell students that actually it serves like a kind of pivoting. Okay, it serves like a kind of pivoting. Okay, whereby maybe whoever that is a fixed point there, maybe there will be some rotation that's ongoing about this particular fixed point, which sometimes I know it as a pivot. Okay, but of course, fixed point can be just like literally like what the name mentions, a fixed point. It's just an anchor point whereby it's actually fixed there and prevent the things from dropping. So whether it's rotation or dropping, I would say it depends on the questions. So by knowing what's the meaning of the labels that I'm giving you, students can actually have a rough guide of how the whole mechanism works. Okay, and in this case, when the current flow through the coil itself, when the current flow through the coil itself, and true enough, when the current flow through the coil, okay, we have a coil and a soft iron core. Okay, the soft iron core will actually become the coil and the soft iron core will actually become a strong electromagnetism magnet. And what it does, okay, and is that this pivoting, the moment it becomes a magnet, you'll find that this iron core will attract this particular pivot or this particular iron lever. Okay, so this iron lever will be attracted. Okay, and how it attract, it will make sure that with respect to the pivot, it will actually rotate clockwise. Okay, so this is what we mean by clue in the labeling. Okay, so the lever will be attracted upwards, and it's not just moving upwards, it's actually rotating. Okay, moving upwards and rotating clockwise about the pivot. Okay, look at the clues. Then after that, the next instances here is that the spring, okay, the spring, okay, will contract. Okay, you'll pull back because it's being stretched. Just now was stretched. So now the moment the pivot is gone, the iron lever is gone, the spring will pull back. And when it pull back, what will happen? Okay, when it pull back, the springy metal will take effect. Okay, the springy metal will be able, when I pull back, the metal will actually move towards the right side, okay, of the right side of the setup. Okay, and it will actually move clockwise or actually move right side, okay, about the fixed point. And when it does, okay, what happened when this particular rod actually moves to the right or move clockwise, you'll find that this contact point actually is open now. This contact point, I will have a breaking point. So once the springy metal move clockwise, you'll find that the contact actually will be open. And as a result, when the circuit is open, you'll find that the breaker will trip. Okay, and the high current, okay, will be will disappear. Okay, the car device will be disconnected. So the high current will be gone. Okay, and as a result, this is how I actually break the circuit, or how I disconnect the appliances from high voltage. Okay, this is how the circuit breaker works. Now, remember the key focus of you describing how the device works is actually take note of the labeling. The labeling actually is a hint from the marker to tell you how does the whole thing, it might works. Okay, one modification, I would say is a standard thing. So you can operate at a lower current, so it's more sensitive, so that it actually starts working at a slower current. The one of obvious modification is actually to increase the number of turns per unit length. Remember, don't write number of coils. The keywords that we are looking at is actually number of turns in the coil per unit length. Okay, number of turns, okay, per unit length in the coil. Now with this, okay, this will be the this will be end of, yeah, right. This will be end of section A. Now for section B, okay, section B. In section B here, we are looking at your AC generator. Yeah, is it AC generator? Yes, it's the AC generator. Now, the AC generator here is particularly interesting in the sense that the magnet is a north-south pole, but they are like not two pieces. They are actually one piece, okay, in together. Okay, so these are north-south pole at this corner here. Okay, so this is the magnet that's inside, and this turbine or this rod is actually being rotated by the wind. Okay, so as the wind comes by, you'll find that the rods will actually rotate. And when it rotates, what happens? Okay, as all EMF induced, your Faraday will take in. As I rotate, the magnet will be moving towards the coil. And when I move towards the coil, what you have a rate of change of magnetic field lines, okay, which is one of the keywords. And when there's a magnetic field lines, there will be EMF induced. And the last thing stated by Faraday is that the magnitude of the EMF is actually proportional to the rate of change. So the faster I spin, the bigger the EMF induced. So this is one thing that we always tell students to take note when you talk about Faraday. These are the 3 points that students need to highlight to the students. Now, take a look at this particular picture here. Now, based on the small picture is the answer. Now, based on the questions that we have here, okay. Now, when the turbine is rotated twice as fast, this is the same as most of the textbook answer, whereby students will have to take note that when I rotate twice as fast, 2 changes will actually occur. You'll find that the EMF induced will actually increase. And when you rotate twice as fast, this is not the only answer. This is not the only changes. The other changes that we have is that the frequency, okay, of the wave itself will change. Okay, where the frequency of the waveform itself will increase. In other words, it means that the period, okay, the period of each wave will actually reduce because I'm spinning faster. So for one cycle now, one cycle takes lesser time. So for one cycle, it means the time for one period is actually lesser, aka the period is actually lesser. And since period and frequency they are inversely, you'll find that the frequency of the wave actually will increase. Okay, so frequency of the wave will increase. And what does this mean when you translate to the drawing? The drawing, it will mean that when I'm talking about EMF induced, it will mean that the amplitude of the wave actually increase. And similarly, when we talk about period of the wave reduces, it means that the wave is actually closer to each other. Okay, and in this case, the question talk about rotating twice as fast, which means the amplitude will actually increase, and not just but increase, it will actually increase by a fixed number twice, double. Okay, and your waveform will actually, your period will actually reduce, and because you have rotated twice as fast, it will mean that the period will actually be shorter by how much? Shorter by half. It will be half the periods. So the t will actually be smaller by half times. Okay, it will be d divided by 2. So there's actually numbers involved here. Okay, so just take note of the answer. Okay, so when amplitude double, so which means if I'm actually at 1, 2, 3, 4, 5 squared. So actually double, I should actually have 10 squares. So actually I should have 10 squared after I double. Okay, I should actually have 10 squared. Now, originally for one cycle, okay, the period is actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 squares. Okay, 10 squares for one cycle. So now my period is actually lower. So which means my period will actually be 5 squared now. Half the original timing. Or first timing was 10. So half of it will be 5. So I know that the period for this particular wave will actually change from 10 squares to 5, will be depicted from changing from 10 square to actually 5 squares. Now, the additional trick that the marker is hidden inside, okay, is that actually the gap between the two waves. Wait, now the wave itself is not just a sinusoidal wave. It actually consists of the sinusoidal wave and the distance between them. So this is actually the period of the whole sequence. So which means that while the wave actually reduces, while the wave period reduces, okay, by half from 10 square to 5 square, the spaces between the wave will also reduce because of the twice in rotation speed. So which means originally I have actually, how many squares am I looking at? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So now the new wave I should have is actually have, the wave will be actually 10 square apart. Okay, so just now was 20 square apart, now will be 10 square apart. Okay, so with this information, okay, you will be able to draw the new waveform here. Okay, so let's put this into the new drawing. Okay, remember the drawing, it has to be amplitude is 10 squares and the period of that wave is 5 squares and the spacing between the two waves is actually 10 square now. So this is what is the final answer here. Okay, so remember the spacing here has to be 10 square. Okay, and the period itself has to be 5 squares. And the spacing between each wave now actually reduced from 20 to 10 square. Okay, so with this will be the shape of your new graph. Okay, for this picture here, for this particular question, I would say the tricky part is that most of the students will actually remember the speed will double, the period will divide by 2, will be smaller by half. But what they always left out is actually the spacing between them. The spacing between them is also affected. That you also be reduced by half. Right, I would say that this is the one section that students will tend to forget or will tend to miss out. So it's good that we encounter this question here so that you can take note of this, and you actually hopefully you will not actually make the same mistakes again. So remember, when you look at the wave pattern, waveform itself, remember to look at all the section of the wave itself, not just the sinusoidal curve, the up and down. Sometimes the space is actually crucial also. Now for the section part, the second part here, we will look at transformer here, okay, which is after AC generator, after being AC generator, now we look at a transformer. Now the transformer here, I would say is fairly straightforward. So this one will be 25 kilovolts. This will be 12 kilo amp. Okay, so this will be a IP, this will be a VP. Okay, and based on the question, you will find that the output is actually 400 kilovolts, which is VS. Okay, now based on the number here, you should be able to identify, okay, the first one is turn ratio. Turn ratio is straightforward, just applying the formula. Remember, turn ratio is NS over MP, not P over S. So NS over MP. So you substitute the right numbers, your answer will come out straightforward. It will be 16. Ideal transformer, calculate the output of the current itself. This is another straightforward question whereby you're looking at, you can just apply the transformer formula, NS over MP, VS over VP, and IP over IS. So remember that there's a swap here in terms of the spacing. Okay, sorry, in terms of the primary and secondary. Okay, so remember the differences. Or sometimes we actually, if you don't want to use this formula, you can go back to basic, whereby we actually look at the power in the primary coil is equal to the power in the secondary coil. Okay, so you can actually do this also. Okay, so if you don't want to use this formula, you can go back to basic. You can write power in primary will be equal to power in the secondary. So this will be IP, VP, IS, VS. So with this formula, you should also be able to find the formula for other magnitude for current also in the secondary coil. Now, same thing, it's a standard. I would say this part E is a standard answer. Okay, the transmission of cable, transmission of power, it has to be done at high voltage. And one of the main thing is actually reduce energy loss in the cable itself. Sometimes I will ask students to actually just go further, one step further, is to tell the marker to say that since the power loss is actually I square R. Okay, so that's why the cable will actually wants to be transmitted at high voltages so that it can be, the current in the flow in the cable can be actually the minimums. Smaller current, smaller power. So minimum high voltage, okay, it will mean I have low current in the cable. And this will mean I will have actually a reduce in heat loss since power is I square R. Okay, so these are the three things that I always tell the students to highlight to the marker. Okay, reduce heat loss, low current, high voltage, and I square R to link all the three together. Okay. Now, 11 on the other hand, 11 will be slightly tricky. Okay, talking about transducer, okay, input and output transducer. Okay, so that function of transducer and output and input transducer, students have to know. Input transducer, the most important thing is that it actually take in other signals, other energies. Okay, and it converted it to electrical energy. Okay, and output transducer will be the reverse. Okay, he uses electrical energy and he convert it to other form of energy. Okay, so this is one of the things that you have to actually take note of it. Okay, and in our syllabus, you will find that input transducer, we actually focus a lot on input transducer, and one of the input transducer we are looking at is actually thermistor. Okay, whereby we look at the thermal energies or the temperature and the difference in them, and we convert it into electrical energy to tell us or to look at to get a certain job done. Okay, based on thermal constraints or temperature constraints. Okay, now thermistor graph, okay, the IR and temperature. Now, when you look at graph, I always advise students, when you look at graph, there's always a few things that you must be careful. First thing first is look at the axis of the graph. What does it mean to you? And secondly is actually to take note of the unit used in the axis. Y-axis here, the vertical axis is kilo ohm. So which means the number here represents not just 15. It actually is 15 kilo ohms, or to be exact, it's actually 15,000 ohms. Okay, so if you need to substitute numbers from the graph, remember to take note of the prefixes. Okay, so it's not just 15 ohm, it's actually 15 kilo ohms. Okay, so when you ever there's graph involved, I always advise students to look at these two things, look at the temperature, look at the units itself. Okay, to look at the labeling of the axis itself. What does it mean to you? And secondly, is actually to look at the prefixes used by the axis itself. See whether is there any kilo, milli, mega, all these things, whereby you need to take note of the zeros. Okay, when you look at it in your mathematics working. Now, for this particular question here, okay, look at the graph at the result of thermistor at 40 degrees. That's an easy one. 40 degrees here, and one look, you'll know that is actually half of it, which is actually 2.5. Okay, 2.5 here, remember 2.5, although I write 2.5 here, but because the unit is kilo ohm, so automatically this guy, okay, the answer here will be 2.5, which is very easy, kilo ohm. Okay, remember the units. Okay, now ohmic. How do I know that the item is not ohmic? Okay, the easiest is, what do you mean by ohmic? What do you understand by ohmic? Okay, you have to remember for ohmic device, when we say a device is ohmic, one of the most obvious characteristic of ohmic conductors is that the resistance is actually constant. Okay, the VI graph is always a constant. Okay, and from here, at any condition, so from here you will know that because, okay, the graph changes, the resistance is actually changes with temperature, and because of it, you'll find that this is what we call a classic example of non-ohmic resistance, a resistor or one ohmic device. Okay, because for ohmic device, I repeat again, the resistance at all cases should be or must be constant. That is what by definition of ohmic. Okay, anything that changes, the resistance change, okay, with temperature, the result of the device changes with different conditions, that device is known as non-ohmic. Now, for the transistor at the top is actually used here. Okay, a variable resistor 7.5K is here. So this is the R, this is 7.5 kilo ohms. Okay, so 7.5 kilo ohms here, then you are fixed to a 20 volts power supply and with a thermistor. So this is your thermistor. Okay, now it's at 40 degrees. Yeah, at 40 degrees, remember the temperature the resistance at 40 degrees is actually 2.5 kilo ohm. So this is 2.5 kilo ohm. Remember the temperature here is at 40 degrees Celsius. At 40 degrees Celsius. Okay. Then from here you determine the current flowing through in the circuit itself. Okay. Now, made a mistake here. It should not be 7.5 ohm. It should be 7.5 kilo ohm. So the question asks for current, so it will be easier V equal IR formula. But remember, I'm using total voltage, the EMF, the total PD. The resistor I need to use should be actually total resistance across here. So since they are in series, you'll find that the voltage, yes, the voltage is 20 volts. That's definitely. The resistance is not 7.5 kilo ohm, not 2.5 kilo ohm. It's a combination of both of them, because total potential difference, I would definitely need total resistance. Okay, so this will be actually 7.5 kilo ohm plus 2.5 kilo ohms. Okay, so that's why the answer is actually 10 kilo ohm. Okay, so 10 kilo ohms. Okay, remember there's 1,000 here. Remember the representation. Okay, it has to appear in your math. Then after that, you press your calculator, you'll find that the answer will be 2 milliamp. So at this point in time, this current here is actually 2 milliamp. Okay, now in this case, now the variable resistor R is connected. Okay, now the setup is slightly different now. Now I'm connected to an electronic circuit. Now, in this case, while the circuit has changed, as in the electronics is connected to electronic circuit, but the device, the setup is still roughly the same, as in this R is still 7.5 kilo ohm. The thermistor is still in use, is still here, is at 40 degree, which means it is degrees Celsius, which means it is 2.5 kilo ohms. Okay, so this is the resistor here as of now at 40 degrees Celsius. Okay, and from part E, I actually calculated the current already. So this is the current in the circuit. Now the voltage in the circuit, the output voltage of R. Okay, I want to find output voltage of R, means I want to find this voltage here. Okay, so I definitely, if I want to find the resistance of R, I definitely need a current flowing through R and the resistance of R itself. And based on the question, the resistance of R is given is actually 7.5 kilo ohm. So this will be your 7,500. Okay, then how about the current? Current, I mentioned already, we actually found it at the beginning. Okay, so you actually can put the number inside here. Okay, so if you, this is what you mean by 2 milliamp. Okay, so 2 milliamp times 7,500, you'll find that the voltage VR will actually be 15 volts. Now for maximum temperature and minimum temperature, so we need to know what are the conditions. Okay, so why is there a need to differentiate maximum and minimum? Is because of the conditions set by the question. Now, based on the question is that the potential of R varies from 6 volts to 10 volts as long as it's working. So which means for R itself, there is a voltage of 6 volts to 10 volts. Okay, so which means if I add particular 6 volts here, okay, it can work at a particular instances 10 volts, it can work also. But just that at 6 volts and 10 volts, the current that flowing through, or the potential difference flowing through, the current flowing through the devices is actually different. Okay, and similarly, if the potential difference here is, if the potential difference is different, okay, the potential difference across the thermistor will also change. At 6 volts, when VR is 6 volts, it will correspond to a particular voltage in the thermistor. And similarly, when the R is actually 10 volts, it will actually correspond to a certain voltage in your thermistor. And like we all know, thermistor, property of thermistor, the voltage, the potential difference of the thermistor is actually correspond to a particular temperature. So which means that at this point in time, when I'm having VTH, green color, okay, you'll find that it actually corresponds to a certain resistance, it corresponds to a certain temperature. Okay, so vice versa for the red color, when the R is 6 volts, it will correspond to a particular potential difference for thermistor, and it will also correspond to a particular resistor in the thermistor at a certain temperature. So in this case, these two cases, the resistance is actually different. Okay, so that's where you have to take note of this. Okay, so now what we are looking at is for me to identify the minimum and maximum temperature. Minimum and maximum temperature, if you look at the sequence, you will actually need to identify what is the resistance value of the thermistor. Why I need resistance value of the thermistor? Because at the beginning of the question, I am given a resistor temperature graph of the thermistor itself. So if I can identify the resistor, I can identify the particular temperature here. Okay, when output is V6, in this case, I'm using potential divider. Okay, the formula to identify what is the resistance here. Okay, so if you look at the circuit here, you look at the question. Okay, so now this is your V, this is your R. Okay, RTH. Okay, this is my R itself. Okay, so now based on the question is when the voltage, the output voltage is 6 volts. Okay, this is 6 volt. It means it's controlled by this particular resistor R, which is 7,500 ohms. Okay, at this instance here, it will also tell us that based on potential divider, it will mean that this amount of resistance, your R plus RT, okay, will also control, okay, a certain amount of potential. Okay, and this potential we know is actually 20 volts. Okay, so if you sub in, based on this factor here, you sub in to your potential divider formula, you should be able to derive at this particular equation here. Okay. Then from there, you manipulate the temperature, you should be able to identify that the RTH needed for the V out to be 6 volts is actually 17.5 kilo ohms. Okay, now some of us will ask that how do we find this equation? Okay, this is what we call I always look at it in terms of ratio, in the sense that you will find that 7,500 ohms, it will actually control is actually proportional to 6 volts. So if I have a resistance of R plus RT, it will be correspond to a certain voltage, and that voltage actually is called 20 volts. So what do? I will just take a ratio of it, a ratio of these two. Okay, the ratio should be the same, left side and both sides. So once I have the ratio between the two, it will look something like this. The ratio on both sides should actually be the same. Okay, this is what I mean by similarities. Okay, now from there, you rearrange, you manipulate, you rearrange this formula. You should be able to arrive at these steps here. Okay, remember potential divider formula, although it looks complicated, but it's actually I would say it's just following proportion and ratio and proportion. Okay, whereby this amount of potential, this amount of resistor control this particular amount of potential difference. A bigger number of resistors will control a bigger number of potential difference. Okay, it's a basic rate and ratio. So from there now, so we go back to 17.5 now. So now I actually located my thermistor to be 17.5 kilo ohms. So what happened here is, like I mentioned before, once I identified the resistor RTH, I can actually identify the temperature because of the graph that's given to me at the beginning. So at this point in time, so once I identify the resistor, I will look for the graph itself. So 17.5 will be somewhere here. Okay, so at 17.5, these particular instances, this is 17.5 kilo ohms. Okay, and it corresponds to 0 degrees Celsius. So this is the first temperature I'm looking at whereby the output is operative at 6 volts. It's still operating. The thermistor temperature is actually 0 degrees Celsius. And if I repeat the same thing for 10 volts, if the operating voltage of the R, okay, the operating voltage here now, I change it to 10 volts. Okay, so instead of 7,500 controlling 10 volts, instead of 7,500 ohms controlling 6 volts, it now actually control 10 volts. And similarly, if I apply rate and ratio, I should be able to get this formula, and I should be able to get my thermistor to be 7.5 kilo ohms. And true enough, if you repeat the same thing, you look at the graph on the top again, 7.5 kilo ohms, it will actually correspond to the maximum temperature of actually the temperature of 15 degrees Celsius. Okay, so now I actually have the two range of temperature that allows the device to work. So at 6 volts, okay, the operating temperature for the thermistor, it has to be 0 degrees Celsius. And when the output increases to 10 volts, the temperature actually increases to 15 degrees Celsius. Okay, so these are the two operating temperature that will allow the circuit to work. So anything in between these two particular temperature, this circuit will confirm be operative. Now, suggest the use of this particular okay, like I mentioned before, any temperature below 15 degrees, the circuit will be operative. Okay, so which is what I mean by it could be like a heater whereby I time it such that anything below 15 degrees Celsius, it will be too cold already. I will need to activate that particular device. So it could be a simple thing like using a heater. Okay, so now this is question 11 now. So let's move on to question 12. Okay, 12 either. Now for question 12 either, based on the question, there are 6 identical resistors, okay, 10 ohm each. Okay, so then after they are arranged in different, they are arranged in some arrangements connected with the light bulbs and batteries. Okay, now based on the question, you are supposed to calculate the effective resistance between AB. I want the final resistance between this AB. Now between this AB, you will find that the resistors are actually connected in parallel first. Okay, this is connected in parallel to this is also connected in parallel, and then both of them are connected in series together. So let's say you look at sum of resistance. Let's say if you don't like the working here, okay, I always like to break it up. So let's say I say this is one set, I'll say this is R1, then I'll say this is one set, this is R2. Okay, so let's say this is R2. So if I want to find the sum of resistance of R1, which are 2 resistors in parallel, so remember the formula is 1 over R plus 1 over R. So you get actually 2 over 10. which is actually 1 over 5. Okay, remember, for working wise, presentation wise, remember if you're summing the resistance, okay, remember to, after this step, you must flip the number because you want R1. You're not looking for 1 over R1. So this will be 5 ohms. Similarly, for R2, R2 is actually 1 over R2 parallel again. So you have 1 over 10 plus all the way plus 4 of them. Okay, so this will be 4 over 10, which will give you 1 over 2 over 5. Okay, so R2 will actually be equal to 2.5 ohm. Okay, take note of the presentation. Then from here, I want the sum of resistance, which will be R1 plus R2. Okay, which will give us 5 plus 2.5, and will be easily 7.5 ohms. Okay, unit and 2SF. Okay, so take note of the working. You can, I always prefer to break up, to find the total resistance. I like to break up into individual step by step. Yeah, if those who are good at your math, okay, you can actually jump or everything, all the working together. Just make sure the presentation is correct. Part B is a straightforward comparison between potential difference and EMF. This one, I would say, is a standard answer that we see from textbook. So I will skip this. Now, state the potential difference across AB. Okay, potential difference across AB. What we are looking at is potential difference across AB, which is here. Okay, AB. Okay, now, as we all know, this is a series resistor. So if you do the equivalent resistance, equivalent circuit, you'll look something like this. This will be 24 volts. This is R1. This is R2. And followed by the light bulb. Okay, connected in series. Okay, this is what happened. And this is supported by 24 volts. Okay, in this case, this is your VAB. Okay, and based on the question, the light bulb voltage actually is given. The light bulb voltage is actually 6 volts. So series, as we all know, the property is that the sum of these two voltages should actually add up to your 6 volts, which is what we mean by EMF should actually equal to VAB plus V of the bulb itself, okay, which is 6 volts. EMF, which is 24 volts. Okay, if you do your algebra, you'll be able to get 24 minus 6, and your answer will be 18 volts. Okay, quite easily done, in fact. For part C1, we are looking at the current supplied by the drive cell. Okay, so I will draw the circuit here, okay, for easy to explain. So you have R1, then you have R2, then you have the light bulb here. Now, based on what we have done is the question here is 24 volts. The potential difference across here is actually 18 volts. And the potential difference across here is actually 6 volts. Now, there are a few ways to do it for current supply. You can use, if I want to use the total EMF, the total voltage potential difference, I should need to use the total resistance of the entire circuit. Okay, because V equal to IR, okay, you rearrange is voltage divided by resistance. If I want to use total voltage, I need to use total resistance. So if I want to use total voltage, which is 24 volts, I will need to use 10 ohm. I will need to use 10 ohm resistance because the total resistance is actually 10 ohms. Okay, if I want to use V18, I will definitely need to find, I will use the voltage across AB, and I will need to find the resistance across AB. Okay, so the voltages and the resistance must tally. Okay, so if I'm using VAB, I need to find the voltage across VAB, which is 18 volts. And the resistance here will be actually 7.5 ohms, like what I mentioned here. Okay, and this will give us the same answer, 2.4 M. Okay, but vice versa, there's a few, the third way that we're looking at, although not recommended, is that you can actually look at using the light bulb. I can have the voltage across the light bulb divided by the resistance across the light bulb. Because I know the voltage across the light bulb is actually 6 volts. Okay, so if I have the resistance of the light bulb, I should be able to find the current flowing through the circuit. But in this case, I will not advise using this because I actually do not have the resistance of the light bulb at all yet. So actually, I will actually stick to either using the total voltage divided by total resistance, or I will stick to just using the resistance, the total voltage across the AB divided by the resistance across AB, whichever is more convenient for us.
And true enough, okay, I actually want to find the resistance of the light bulb. Okay, so once I have this equation, you'll find that once I have resistance current of IB, I have the voltage 6 volts, I can actually calculate the resistance of the light bulb, which is 2.5. Okay, so for circuit questions, is that you have to just take note is that there are actually a few ways to solve. Some particular sections from some current, some potential difference, there's more than one mathematical working for it. So it's actually a good news for us because we can actually check, okay, use different method or use different approaches to actually check the answer. Like what I mentioned before, if I use these two approaches, okay, there are two approaches here, okay, I can actually use them to check answer to make sure that current supply by the dry cell is actually correct, okay. Then after that, we move on to the last part. Last part, part D, why is the earth cable needed? Oh, okay, this is an easy answer. Okay, this answer is, I would say, it's a very text-based answer. So definitely, I would say it's definitely doable for everybody. Okay, so question 12 either, clear. Now, 12 all is on the lens, converging lens. Okay, particularly we are looking at is a virtual image. Now, the virtual, when we talk about lenses, there are 6 diagrams that students have, you have to be well versed in drawing the lens, the ray diagrams for these particular 6 images, 6 categories, okay, and you need to take note of the properties formed by the image for these 6 scenarios and the users and applications. Okay, in case you forgot, I actually place a section of it at the side of the video. You can take a look at it. And in case you forgot how to draw a lens diagram, I actually included a particular section. Yeah, I just included my video on lens drawing diagrams in the link below, in the link above. Okay, if you want, you can actually click on it and do a quick revision before attempting this question. Okay, so if you have done your revision and you are okay, you are well versed with the ray drawing diagrams, the 6 scenarios, you'll find that actually 12A and 12B is actually quite doable. Okay, so that's why I will not say it's difficult. It's actually quite standard in the sense. Okay, the only thing that students you have to take note is that there are some that you need to use rulers. We need to draw it with precisions. Okay, so for this case, I will not go through this question since I think it's actually quite normal and most of you shouldn't have a problem. But in case, okay, you need to check your answer, or in case you're not confident about your answer, okay, do drop me comments after the video finish so that I can get back to you. Okay, or if you need me to go through this particular question, just let me know also so that I can actually upload a video on this. Okay, if not, okay, we look at part B. Now, part B are the characteristics of the image itself, okay, which is, like I mentioned before, if you are well versed with the 6 diagrams, the 6 properties, or the 6 characteristics of the 6 scenarios, okay, you should be able to answer this actually quite with ease, okay, because remember the 6 scenario which I leave on the video right now, you see that it actually encompasses on us the characteristics of the image, the application of the image, and actually different scenarios of the images. Okay, so for example, how do I know how do I know which particular scenario I need to use for part D? Okay, it's because based on part D, I actually has certain conditions. I need identical copies, meaning the object and the image is actually the same size. Okay, now if you look at object, same size as image, with this particular condition, it will actually give us a particular scenario in the ray diagram whereby the object and the object has to be exactly at 2 focal length away, or somehow what we call 2f away. Okay, you can refer to the 6 scenario by the side. Okay, and this is what we're trying to tell. I'm trying to tell you is that the 6 scenarios are actually standard 6 scenarios. So given the question, if you are well versed with the 6 scenario, you actually know where the question is heading. Okay, so in this case, if it's exactly the same size, okay, there's only one particular scenario, it has to be 2f away from the lens. Okay, so your object has to be 2f, because only at 2f you have image producing exactly the same size as the object itself. Okay, and law of refraction, actually, I would say this is a quite standard question. Okay, so and this happens to be the last part of this particular question. Now for 12 either and 12 or, I would say both of them are like, I will not say they are difficult, but it's definitely something that students need to know. Okay, they have to be good at their basic and their foundations in order to attempt 12 either or 12 or successfully. Now, same as before, okay, for this particular video is that, for this particular paper, if either and or, okay, please read the question carefully first. Both questions, read both questions. Okay, don't just read the first one and you just attempt it straight away. Okay, remember to read both questions first and choose the question that you are more confident with. After that, do that. Okay, if not, this is the end of paper 2. Okay, if you need a paper 1, okay, I will be going through it. Okay, I will leave the link on up on my video so you can go and refer to it if you need the paper 1. Okay, we have come to the end of this video. I do hope the video is useful for you. At least it might have actually made your learning of physics much more enjoyable and easier along the way. Okay, if not, okay, stay tuned for my next video. Bye bye.